Welcome everybody. I'm now sharing my screen. You should be seeing the title page for Quantum Physics for Everyone, Week 2, Day 2. So today we're going to be continuing our discussion about polarization of light, both the classical and the quantum description of light polarization, dealing with light waves and single photons. And also we will be doing some Jamboard exercises. And then we'll discuss the more general question about qubits. What are qubits in quantum physics and quantum information science? So here we are in our outline of our 9 key concepts that define quantum information science. We'll be discussing both of these green topics today. Okay, so I just wanted to start with a review. Recall that a calcite crystal sorts light by its polarization. So if we have some light here of an unknown polarization, could be a mixture of different polarizations. And if the light passes through a calcite crystal, it gets split up into 2 separate beams, one corresponding to vertical polarization and one horizontal polarization. That's because the way the calcite crystal is oriented. If we rotate this crystal to 45, then the same crystal will be sorting light according to diagonal and anti-diagonal. And in fact, we can rotate that crystal to any angle that we wish and analyze in that different measurement scheme. Or we can use a plastic film polarizer. And this is similar to the calcite crystal, except it blocks or absorbs one of the polarizations and it's lost forever after that. We can no longer recover that because its energy has been deposited into the plastic film. But one of the polarizations in this example here is H, which passes through. Ideally, a really good polarizer would pass nearly 100% of the light. The plastic film polarizers that we sent to you probably only pass about 80 or 90% because they're just not very expensive devices. So a polarizer film is similar to a calcite crystal where one of the output beams is blocked. Okay. Then we talked about what is a quantum state. It's representation of everything that is possible to know about a quantum object. And in quantum physics, we cannot know everything about an object in the sense that we cannot describe the properties as actual properties that exist prior to making a measurement, as we could in classical physics. But in quantum physics, the state description allows us to calculate probabilities for random outcomes of measurements. And we believe that these random outcomes or behaviors are inherent in nature and that there's no underlying hidden mechanism that's creating this randomness. Unlike in classical physics, you can have a situation where we talked about in a case where a baseball is hit and it flies past a wall, through a wall, could go through one of 2 different holes. In that case, that's what we call classical uncertainty. We still have probabilities to discuss or describe which hole the ball likely will go through or did go through in the past. But those probabilities are very different than quantum probabilities because those classical probabilities represent the probabilities of actual events, which actually happened, we believe. But that's not the case in quantum physics. If you're not observing something on a quantum object, you can't really say that something happened before you observed it. So this, of course, seems very non-intuitive, but this is the best way to think about what the quantum theory is telling us. So then how do we use these probabilities? We use the Born's rule. And if we have a polarization axis shown here, we project our state at a right angle down onto that axis. We measure the length of that, A. And of course, the length of the state vector is always 1. So then we take that A, we square it, and we get the probability that the outcome will correspond to that axis, like in a calcite. The other axis is called the complementary axis. And B squared would be the probability for that axis to be observed, or the photon to be transmitted on that axis in that corresponding beam. And of course, these probabilities add up to 1. Okay, so here is a zoom pole. A single photon enters a polarizer. Here it is. It has a polarization of -A, and it goes to a vertical polarizer. And now I will load the pole if here it is, launch pole number 1. Please answer this. Okay, I'll share the results. And we're seeing that most people believe that it is D, which says that 50% transmits and the polarization will be vertical, which corresponds to the polarization axis. A few people thought that 100% of the light would go through this polarizer, but that's not correct, because you only get 100% going through the polarizer if the polarization state of the incoming photon matches to the orientation of the polarizer. Then ideally 100% would go through. So that can't be right. And the other one that's not correct is that if one says that 50% goes through and then it would point D, that wouldn't be correct, or AD, that's not correct either, because we know that the polarization of any light that passes through the polarizer has the same polarization that is defined by the polarizer axis. So I'm going to click through this. And so it should be, really should be V. Oh, sorry. Right, it has to be V. So 50% goes through and it's V. So this was meant to be a warm-up question which reviews the previous couple of sessions. So please review that and get clear on that. Here's another Zoom poll question. This one's a bit more lengthy. Consider sending a photon. Let me just go to the Zoom poll here. Zoom poll 2, launch the poll. Okay, it's a bit lengthy. I'll just let you read that. Let me just give a hint. This is the polarizer axis here, and this example is vertical. This is the state vector or state arrow. This is the angle between those two. And imagine what would happen if this state vector were tilted all the way up to the polarizer axis, perfectly parallel with it. That should give you a hint as to which of these answers is correct. And good, I see some people adjusting their answers, which is in the right direction for the answer. And the latter half of the question has to do with what we talked about in the previous Zoom poll. Now again, remember, the light is polarized this direction as the red arrow. In order to calculate the probability to go through the axis of the polarizer, we project it on to this vertical axis, and we calculate the length. And if the axis of the original photon polarization is not the same as the polarizer, remember, only the component of that state vector that is parallel to that will be transmitted. Therefore, in this example shown, the state of the photon polarization would be changed if it passes through this vertical axis polarizer. The only case where it would not be changed is if the state were already parallel. Like, oopsie, sorry, it's not editable. Okay, so I can share these results. And I can see there's still some confusion here among the poll respondents. That's why we do these polls, right? It's to make sure if we really are following what's going on. And, you know, if you have a wrong answer, that's nothing to feel bad about. It just means you have some work to do. And, you know, that's how science works. We just explore all the possible answers, and we keep thinking about the theory and experiment until those two agree and we get the right answer. So what I show in this cartoon here is that in this example, the polarization of the original photon is the red arrow. After it goes through the polarizer, it's now the green arrow. If it doesn't get through the polarizer at all, then there's no arrow at all. There's no photon, so there's no state. So if it does get through it, it's going to change it, just like in the previous example. I'm going to stop that. Stop that. Just like in this example. Remember, if the photon gets through the vertical polarizer, its polarization is now vertical. That's a really key point, because in quantum physics, there is no predetermined actual polarization of the photon as there would be in classical physics. There's only a quantum state, which is represented by this blue arrow, which tells you the probabilities that the photon will pass through the polarizer. But we also know that when if it does pass through, it's going to have the same polarization as the polarizer. And now the state has actually been changed by the very fact of going through this polarizer. So that's really crucial to get this point. That's why I'm belaboring it quite a bit, because that's one of the fundamental properties of quantum physics, which leads to all the quantum technologies, quantum computing, and so on. So now let's move on to the Jamboard. We're just going to be reviewing some of the things that we worked on last time. I think it's important to go slowly enough that everybody is up with us. And if there's two ways to solve these problems. One is to draw a picture, you know, draw the lines on the Jamboard and then measure the length just by counting the fractions of boxes and squaring it. The other is to use the cosine squared of the angle. So if you're a little more advanced on the math and you understand the box counting method already, then go ahead and work on the trigonometry solution. Cool, okay. There are correct answers on every page, that's fantastic. So let's go now to the next question, which is on page 5, starting on page 5 of the Jamboard. And I showed 2 graph papers there just to give at least two people a chance to draw pictures on there. So you're not competing. So now this is the same problem that we worked on at the very end of the last class session. So if you know you got the right answer on that, why don't you hold off and let somebody else attempt the problem if they're not sure. But after a couple minutes, if you don't see the right answer in there, you can chime in and help out. Okay, so now we are back to page 5, 6, 7, and 8. And I see a nice attempt on page 5. That's very good. We project first onto the H, then onto the A, then onto the V. Okay, page 6, somebody can attempt an answer there. Page 7, somebody should attempt an answer. And page 8, the same thing. And if you're not quite sure how to do it, look at page 5 so we can move along. Okay, making progress. Now we need to project from the new state vector on the H axis over back to the minus A axis. And then if we do it precisely, yeah, then we can estimate the length of the vector on the final V axis, which is where we are, and then we square that. Mm-hmm. Okay, if you're stuck or not sure how to get the drawing to work, whatever, go ahead and put a comment in the chat window, because I would like us all to be up to speed on this. Mm-hmm. Okay, I think I know a number of people have it worked out perfectly. A number of people are still struggling, but that's exactly to be expected, you know, in a course like this, right? So what I will do now is, instead of spending more time on this, let's go back to the slides. I can't seem to go back to my slides. Give me a second here. Okay. So here we're back on the slide, and that's the previous one. So we did the previous one. We projected down from the state arrow to the H axis. The new state arrow looks like the green one. It has a length of 0.92. And then here's the formula. 0.92 squared is 0.85. And that is the probability that the photon will pass through the H polarizer. That's called Born's rule, the most important rule probably in all of quantum physics. For those who like trigonometry, you could also do it this way. The angle from V to H is 90 degrees. Therefore, if this is 67.5 degrees over there, then the angle between H and the state vector is 22.5 degrees. So if you take the cosine of 22.5 degrees, oh, and notice I was making a mistake when I went into Google to calculate this cosine. If you don't type in degrees here, it thinks you're working in radians and you get the wrong answer. So you have to say cosine of some number in degrees. That gives you 0.92, which is the same thing that we estimated from our graph paper. And then you square that and you get 0.85. Okay, so if you're, if you're still struggling with this a little bit, please go back and review these slides because I will post these, after today's session. And now here is this next problem with the three polarizers. And remember, we did that experiment with your polarizer last time. If you have the H and the V polarizers only, and you don't have the A polarizer in there, then nothing gets through because they're perpendicular, they're mutually exclusive. So why would that be? Let's consider that. If you start with A and you project on the H, you'd be here. And then if you project on the V, it would send you all the way down to the origin. So the length of the vector would be 0. So 0 squared is 0, so the probability is 0. That means nothing gets through. But then, interestingly, when you put in the intermediate polarizer, you first project from the tip of the state vector down to the H-axis. That has a new state vector, which is a length of 0.71. Then you project that state vector back to the A-axis. And notice the A-axis is this entire minus A plus A line. And if you go straight at a right angle to it, you get here. And the length of that is about 0.5 if you know how to figure that out. We don't need to know that exactly. But then the next step is you project that point over to the V-axis because that's what this polarizer is. And if you estimate that 1, 2, 3.5 boxes, you get about 0.35. And then you square that and you get 0.125, which is actually 1/8. Some person actually put that onto the Jamboard, which is a good point. It's exactly 1/8. Now, why is that? Well, in this case, the probabilities multiply because each of these events is independent. We first filter with this one, then we filter with this one, then we filter with the third one. So the probabilities multiply. So you can think of it in various ways. 0.71 times 0.71 times 0.71 squared. This whole product here is 0.35. That's what we got from this picture here. And you square it. But that's the same thing as the square, as the product of the squares. But the product of 0.71 squared is equal to 0.5. So 0.5, 0.5, 0.5 is 1/2, 1/2, 1/2 is 1/8. So you can see in this particular case, the probabilities multiply. And here's a more mathematical slide, just laying that out. In the X here means times, means multiply. Why do we do that? This just repeats what I said on the previous slide. I just want to have it really, clearly written out in words for you. So in that case, the total probability of all three events happening, namely going through all three polarizers, is the product of three individual probabilities. That's because it's a sequence of independent steps. However, in some other cases that we'll see next week, we don't do it that way. We need to first add the lengths and then square. And this is called quantum interference. And it's probably the second most important concept in all of quantum physics. But we'll postpone that discussion. Now I think you should just understand this previous business about multiplying them together. And again, please feel free to throw in questions into the chat box or just unmute yourself and interrupt me at the proper moment. Okay, so here is a homework problem. As I explained in the emails, the homeworks are additional problems which are meant to be a little harder, and they're completely optional. I'm not pressuring anybody to do those. But remember, I am pressuring you to do all the Flexi quizzes. So here's a nice problem. What if we just have, what if instead of having one polarizer here between these crossed H and V polarizers, we now have two polarizers, and we're free to rotate those polarizers to any two different angles that you wish. Now remember that without this polarizer here, we get nothing through because the H and V are crossed. But if we put one polarizer in, we can get, like we just calculated, 1/8 probability to go through. The question is, can you put two polarizers in there, rotate them to the perfect angles, so you can get more than 1/8 probability of the photon to go through? It's a fun problem. It's just a simple generalization of the previous Jamboard exercise, but a little more open-ended because I don't give you the angles initially. So if you want a more challenging problem, please work on that one. And if you can't figure that out and you want to, send me an email and I'd be happy to chat with you about this on email. Okay, now new topic. This is a question just for general discussion. I think it's a Jamboard. I'm not sure if I set it up that way, but in this course, we're gonna see a few characters. One of them is always called Alice, and one is always called Bob. And quantum physicists love to pick funny pictures for Alice and Bob, so that this is our current choice here. It's because we could then talk about these two people as protagonists or actors in a scenario. So in this scenario, Alice prepares a single photon, but does not tell Bob what the photon's state is, but Alice knows what the state is. Now Alice sends that photon over to Bob, and only one photon is sent to Bob. And the question is, can Bob determine the polarization state of the photon that was sent to him? If so, how? If not, what can be done differently? So go ahead and type some answers that you think might be relevant to this question. Okay, and answer the second part of the question as well. And I'm not going to tell you what the correct answer is now. Some of you can vote for different answers, because this question was not obvious, I would say, maybe say 30 years ago in physics research. These kind of questions were not really even considered 30 years ago or 40 years ago. But yeah, if you agree with an answer, you can put a check mark there, but you also have to answer the second part of the question. Yeah, explain why you cannot, or why you can, or how you can. But let's say that Alice does want Bob to know what state Alice is preparing. And let's say that Alice can only send individual photons, not a laser beam, not a high power laser beam, but good. Those answers are all perfect. Except the one in the upper left corner here is so he can try to determine the probability of polarization in two mutually perpendicular directions, then the square root of the ratio is approximately the polarized angle. This is a very good point, but if you do it for a single photon, if Bob does it for a single photon, it fails, because as other people pointed out here, the first measurement makes the photon forget, as we learned in the last class, the word forget. It forgets what its original state was. Therefore, making a second measurement on that single photon doesn't tell you anything. And that's why other people made the comment that Alice has to send a beam of photons, then Bob can make recursive measurements, but it's not recursive on a single photon. Right, I forgot, one photon. Yeah, Bob doesn't make recursive measurements on any single photon. He always takes a new photon and makes a set of measurements, well, makes one measurement on each photon, and then repeats that maybe 1,000 times on 1,000 different measurements. Cool. Okay, so that's a really important point there, okay? The reason it's important is because this inability of Bob to measure the state of Alice's photon is actually what gives us security in quantum communication systems. So you've probably heard, statements that we can do quantum cryptography, or we can make information transmission perfectly secure using quantum techniques. And that statement is at least theoretically true. And we believe it's true. And it relies on this fact that if an eavesdropper gets in between Alice and Bob and grabs the photon and measures it, the eavesdropper cannot actually tell what state Alice sent, because Alice would be smart enough only to send one photon and not to repeat that photon. So we'll talk in great detail in the next class about how quantum cryptography works. So yeah, it's pretty cool. I think it is pretty cool. So let's go back to my slides there. And right, this just now summarizes what we just said. So now we're going to talk about the concept of quantum bits. Photon polarization is a very nice example of quantum bit, but it's not the only important example. Let's first talk about what are bits in the classical computing context. So in classical or digital computing, a bit is any physical object that can be in just one of two possible states. And those are classical states. And so in the lower left side, I showed dynamic RAM, random access memory, which is in your computer, in your phone and everywhere. And each memory location is a capacitor. This little tiny 2 lines here, of course, is a electric capacitor, and it can hold a certain amount of charge, which classically would correspond to maybe a few hundred electrons, which would give it a negative charge on one side. And so if any one of these capacitors holds a charge, we designate that as a 1, a mathematical or logical 1. But if the capacitor holds no charge, 0 charge, we designate that as a logical 0. And we have an array of these things, and of course in your computer you have something like well, I don't know, 10 billion of these little capacitors, and you can access each one randomly. That's why it's called RAM, by using these control lines. So you can write data into here, and you can read them back out using these cross control lines. So that's how you store information in the classical computer. Now, how do you transmit that? If you make a cell phone call and your phone sends out a radio waves, how does that work? Well, there's a carrier of voltage. This is a voltage versus time on this axis, and a simple radio wave would just have a single tone like that. Maybe it's 5 gigahertz frequency, which is a radio frequency. And then in order to imprint information on that, you control the amplitude of this oscillating radio wave with this control logical signal. So if this signal voltage is 1, that multiplies this by 1 and gives us a little data pulse, which represents a 1. But if this control signal has a 0 voltage during one of these data periods, it multiplies this radio wave by 0, and so the amplitude is 0. And so the final signal that gets sent out from your phone out to the cell tower looks something like this. And of course it's sending, billions of these well, I should say millions of these every second, these little pulses. And then of course, it's the sequence of ones and zeros, which carries the digital information. But the point is, for classical communication, each of these objects, either the radio wave or the capacitor, is described by a classical state, which means is it actually in one state or the other. You may not know what it is until you measure it, but it's in a definite state. And you can measure it more than once because the state doesn't change when you measure it, ideally. Therefore, you could clone it, you could copy it, and we know it works, right? You have a copy machine in your office or your home, and you can run a piece of paper through it and make copies of it, or you can obviously do that on a computer. So you can copy these as many times as you want without degrading the information. That's very different than a quantum bit, as we'll see. You cannot copy a quantum bit. Okay, so what do we do classically with these bits? We can write words, English language words, and here's the standard American code. It's called ASCII, A-S-C-I-I, and each letter of this Latin alphabet is represented by an 8-bit sequence of zeros and ones. So going back over to here, if I send 8 of these, here's a 1, 0, 1, 0, 0, 1. So 1, 2, 3, 4, 5, 6, 7, 8. Those first 8 represent a sequence of bits, and those would map onto one of these. I don't know which one, maybe it's this one, for example, represents the letter H, the lowercase h. So that's how we encode, language words into mathematical or logical signals. Good. Now, quantum bits or qubits are, of course, totally different. They still require a physical object to be represented or to represent them, but these objects are quantum objects. So they cannot be described or prepared in a classical state, and they're subject to no cloning and no perfect measurements. But you have to describe the probabilities of measurements. Okay, it's called the qubit. Right? You can use a polarization state of light, as shown down here. We have V pole and H pole. You can specify, and you can choose this yourself. If you're the engineer building the system, you can say, I define H pole to be a 0. I define V pole to be a 1. And then if Alice, we always say Alice and Bob, if Alice sends a sequence of these photons to Bob, then Alice is sending a sequence of quantum bits, quantum information. But strangely enough, as we just said, Bob cannot actually measure that information reliably. So you might think, well, that makes it kind of useless, but actually it doesn't, as we'll see later. In other words, one would not use quantum bits in this manner. You would not use them just to send a message, like, hi Bob, encode that. That just wouldn't work. But there's other things we can do with it. Now, we also know it's possible to make D and A polarized single photons. Now that's very cool because a depolarization state now is a quantum superposition of 0 and 1. So if Bob measures that in an HV basis, Bob could get 0 or 1. Now, or Alice could prepare a polarization state, which is also a superposition of 0 and 1, which is actually a different superposition. We know from our arrow diagrams. Now, you might be thinking back over to here, you might be thinking I said something wrong. I don't know if you remember exactly what I said, but I'm thinking that I didn't explain that quite correctly, which is good because it's a test for you to try to figure out what I might have said wrong. I said that if Alice sends V and H photons over to Bob, there's no way Bob could receive that message because he couldn't measure the single photons. But I left out one important fact. If Alice tells Bob in advance that every photon I'm sending you is H or V, and I'm never going to send you any other kind of photons, Now Bob has some prior information. Bob can set up a measurement device like a calcite crystal. And now I'll let you think about this for a second. Can Bob now receive the message perfectly? I have an idea. What if we went to the chat box? Would that be a good option? But if we went to the chat box, everybody has the chat window. Can anybody type in for everyone an answer to this question? The question is, can Bob receive a message perfectly if he knows in advance that Alice is only sending V photons or H photons? Yes, I agree. That's right. Because we know if Bob puts a calcite there that's oriented in the correct manner, namely HV analyzer, then each photon will go through perfectly and predictably into the right detector. Good. I'm glad I made that mistake because now we had to explore it. Now going back to the second part, if Alice instead sent depolarized photons and apolarized photons, and she said, oh, now a D represents a 0 and A represents a 1, she could think that in her own mind. But if she didn't tell Bob that she had changed her measurement scheme, now to D and A, and Bob was still using H and V crystal to analyze, he would just get total random garbage. Every photon she sent would have a 50-50 probability of coming out in the H detector or the V detector with carrying no information whatsoever. So that means that Bob and Alice have to agree in advance. And this agreement is called a protocol. The protocol is something that's well known in computer science, in classical computer science. It also applies to quantum protocols. It's like a methodology. Okay, I'm going to close my chat window now and move on. Before I move on, let me go back to these comments in the blue boxes here. We already understand point A about superpositions, but point B is also reminding us that if we have n classical bits, remember on the previous slide, I showed, for example, here's 9 classical memory cells. Now, each of those can be in one of 2 states. So the number of possible combinations is 2 times 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 2. That's 2 multiplied by itself 9 times, which equals 2 raised to the power 9, which is a large number. So that means that this set of 9 memory cells can contain a very large number of possible words, if you like, or patterns. Okay. That's also true for quantum bits. If I had 9 quantum bits, like 9 photons, you could also record or store 2 to the 9 classical bits. The reason I say classical is because, as before, if Alice and Bob are using the same measurement scheme, then the information pretty much boils down to classical information. But as we'll see later, Alice could do something much more tricky than creating each photon and sending it separately. Alice could create entangled states among several photons, or even all 9 photons. And this is something that's impossible to do with classical bits. And it's an entanglement among many photons or many qubits that really gives the power of quantum information. We'll discuss that later. Okay. So now looking at the state arrow representation, I'm just reminding you, it's a nice little picture that I drew for you. You know, here's a psi vector's H. Here's a psi vector that's V. Here's a psi vector that's V, which is 0.71 V plus 0.71 H. And here's a vector that's A, which is 0.71 V plus 0.71 times minus H. Because remember, minus H is the arrow that points along this axis, to the left. So I'm just reviewing this notation so you'll feel comfortable with it as we go forward. Now we're going to change gears completely and talk about electrons. So you probably all know that electrons are you know, essentially point particles that have mass, small mass, but they do have mass, as compared to photons, which don't have mass. Photons have zero mass. Electrons, each one has a small mass. It has negative charge. It also has intrinsic spin, which I like to make a little cartoon. Like you think about that little metal spinning top there. You can spin that top counterclockwise or clockwise, depending on how you spin it. And the spin is with respect to what I call over here on the right, the up direction. Because when you set a top onto a table, that's you're going to spin it. And if you're really good, you can make it spin exactly vertically or up. And that's relative to your frame of reference. And normally the frame of reference is defined by gravity for a top. But for electron, gravity doesn't play any role, really. And so you have to define what you mean by the up direction. That's your choice, but I'm always going to draw up direction pictures in the, you know, up direction on the screen. Okay, now, so it carries angular momentum, which if you spin a top, it has a persistence of rotation. It's going to keep rotating until something, you know, forces it to stop rotating, like friction. So a spinning electron has that same kind of angular momentum, persistence of rotation. Now, if you have many spinning electrons in a metal, you can create a magnetic field. You know, the metal becomes a magnet. So what that means is that each little spinning electron itself creates a tiny magnetic field around it. And if you have a billion spinning electrons all with the same orientation, they create a macroscopic magnetic field, which you can use to pick up metal objects with. Okay, I think most people know these properties of electrons. But now, let's talk about electron spin as a qubit. So it's not the electron that's the qubit, it's the spin of the electron that's the qubit. That's what codes it. So we have this electron. We can define, because we're the engineers who built the machine, we can say, I define spinning clockwise as a logical bit value of 1. And I'm going to define counterclockwise spin electron to represent a 0. So if I send you a sequence of electrons, and if you could measure their spin, and each one was counterclockwise or clockwise, you could then decode the sequence of zeros and ones that I sent to you. Or if I put these electrons into a quantum computer memory, I could use those to store quantum information and do quantum computations. Now, as we know, quantum objects can be in quantum superposition states. So I can create a single electron, and I'm going to say a very wrong way to say this now, which is always said in the media, which is wrong. You could create an electron which is both spinning counterclockwise and spinning clockwise at the same time. I'm sure you've probably heard it said that way. That's actually wrong. It's a nice way to explain it, you know, to your neighbors who don't know quantum physics, but it's wrong because it's not true that the electron is spinning clockwise or spinning counterclockwise, and it's also not true that it's spinning both directions at once. It's simply the wrong language. There's no language of that type that describes the quantum state. The only language that's correct is it's a quantum superposition of both quantum possibilities. Okay. So here I show, again, I show this picture of H and V for the photon, and we're quite comfortable with that because H, you know, for the photon points in the horizontal direction, V for the photon points in the vertical direction, because that's the way that these polarizations actually exist, you know, in the laboratory or in the real world. But now here's a huge leap. If you haven't ever considered this before, you should recognize this as a huge conceptual leap. We're now going to represent a counterclockwise spinning electron with a state arrow that points in this, I'm not going to call it direction because it's not a physical direction. It's a state arrow that points towards the label CW clockwise. And if I have a counterclockwise spinning electron, I'm going to represent that by state arrow that points towards the label counterclockwise. And this is the mathematics of quantum physics. This is called quantum state space. And you have to become comfortable with this more abstract way of representing states mathematically. And of course, really we use equations, but I'm always just doing everything graphically. Okay. So the photon state actually points in real space the same as the polarization, whereas the electron spin state vector points in what I'm calling an abstract space. I haven't exactly figured out a good Jamboard question for this. Let me see what pops up next here. All right, we'll skip it as a Jamboard exercise. So here is the application now, the usefulness of this abstract representation. I told you that we can represent the clockwise quantum state by an arrow that points towards CW, and a counterclockwise spin state that's an arrow pointing towards CCW. Well, I told you also that you can make a quantum superposition. The electron can be created in a quantum superposition. Well, I think you should probably guess pretty easily now that we can represent that by an arrow pointing in 45 degrees, whose projections are 0.71 on the A value and 0.71 for the B value. And the sum of the squares adds to 1, as it should. So this is the abstract quantum state mathematics that underlies everything. And of course, I could tilt this state vector so it's pointing closer to the B axis, or I could tilt it so it's pointing closer to the A axis, which really means I have to prepare that electron in a particular state of my choice. And then I can describe it by this green arrow drawn on this little piece of graph paper. So of course, what it means is that if I prepare my electron in a quantum superposition, and then I have a device that can measure whether the electron is spinning clockwise or counterclockwise, and I measure it, think, what's the probability that my measurement device will tell me that it's spinning clockwise? I think you know the answer by now. It's just like the same mathematics as the photon. Because the length to this is 0.71, I square that, I get 0.5. There's a question, can you talk briefly about how do you prepare electron in a superposition state? There's various ways to do that. Because the electron, actually, I'm going to try something here. I'm going to try going over to the Jamboard, if I can. I'm still sharing my screen. So if I go onto a Jamboard page, here's a nice blank Jamboard page. I'll get rid of that. So if you don't see the blank Jamboard page, it's 15, but I'm sharing my screen, so you should see it. So let me draw something. If I have some device here that spits out electrons, and that could just be a hot wire. In fact, if you've ever used a CRT screen, a cathode ray tube, we used to have televisions that were made with cathode ray tubes, and what they were, I'll just do a little digression here. A cathode ray tube. There's a cathode. A cathode is a hot piece of metal that spits out electrons. And then on the front of the viewing screen, what's it called, a phosphor. And if an electron strikes a point on the phosphor, it emits a little bit of light. So when you're over here with your eyeball looking at it, you see that. Okay. So that's how you make electrons to begin with. Okay, so let's say we have now a hole in a screen. So we have some electrons coming here. Now those could be spinning clockwise or counterclockwise. So let's say we just have one electron. How can I prepare it? Well, it's actually pretty hard to prepare it directly, but here's what you do. You set up a magnet. You get a horseshoe magnet. As a north and a south pole. It turns out, this has been known for 100 years, that if the electrons are spinning clockwise, they'll be deflected up. If they're spinning counterclockwise, they'll be deflected down. That's because each electron is a tiny magnet. So when it goes through an inhomogeneous magnetic field, it gets deflected up or down. Yeah, we're going to block that. We're going to block that. And then what we're going to do is we're just going to take maybe another magnet here somehow and bend that beam like that. And now we have an electron that's counterclockwise spinning. So it cannot prepare it perfectly every time, but you know that when you do have an electron here, you don't know when it's coming out, but when it does come out, it's counterclockwise spinning. And then how do you measure it? You put another horseshoe magnet here, and you measure it, and now it's going to go up again because it's still counterclockwise. But now the trick is, so this is called I see there's a question in the chat, I'll get to that. This is called the z-axis. And I analyzed this here with a horseshoe magnet, which is the same axis as the preparation one. So if it went up the first time, it's going to go up again the second time. So going back now to the slides, the difference here is what I was saying there. I think I have to go to this slide here, and then this slide here. Okay, so now here's a little bit more challenging problem. But it's very much analogous to the photon problems that we did earlier on the Jamboard. So electron spin is in the superposition states shown, the green arrow, with an angle here of 22.5 relative to the state which represents clockwise. Its spin is measured to either be CW or CCW. What is the probability to observe it to be CW? And I put this little comment in the upper right-hand corner with respect to the up direction. That just means that CW and CCW are measured as spinning relative to the up direction in the laboratory. That's the detail, just don't worry about it. So looking at the diagram here, if you know this is 22.5 degrees, you can either eyeball it. Why don't I create a Jamboard for this? Let's go to the Jamboard, page 16, just the next page from where we were. And what I'm going to do is paste that image into there. This is actually pretty efficient. Right. So work on page 16 of the Jamboard, which I'm also sharing my screen now, and go to your Jamboard and type what you think the answer might be. I mean, show your calculations if you can. I just made it larger so you can actually count the boxes if you want. And you can still put notes on top of this page here. Yeah. I see one answer has appeared. I'm not saying if that's correct or not. It might be. I just realized that my little green arrow that I drew in the graph paper does not actually have the correct length. Its length should be 1, but I drew it a little bit too short. And the purple line is a little bit too short also. So if you understand what's going on, you'll see how to correct that. I wasn't planning to make this one a quantitative exercise. You can agree or disagree with answers that are being posted. I'm fixing the arrow a little bit. Yeah, but I think you're all on the right track anyway. Good, everybody's agreeing with those answers, and I also agree with those answers. It's the same calculation we did before with polarization, but again, to hammer the point home, these directions and angles have nothing to do with directions in space, like the directions in your lab or the orientation in real space. This is a purely mathematical exercise using vectors and projections and squaring the number, and the formula that's given in the yellow box here is correct. It's still cosine of 22.5 quantity squared. Very good. So now we've taken you from photon polarization, which can be understood pretty intuitively because the states correspond to actual directions in the laboratory and the directions of your polarization analyzer devices. We've taken you from that into a more abstract mathematical case where the states are represented purely mathematically with the same mathematics, the same superposition, the same Born's rule. It's just that now the states don't correspond to directions in space, they correspond to counterclockwise and clockwise, which is not a point in a direction in space at all. It's just the way the thing is spinning. So now once you think about that, you can generalize this to many other examples. We have another couple minutes. I'll just improvise here. I'm going to go to a new Jamboard. Let me know if on the shared screen, let me know if you didn't see that I just went to page 17. I'm now on page 17. So let's consider an electron, which is my electron is red. And let's consider two boxes. Here's two boxes. Now my electron, if it's in box 1, I'm going to call that box 1 and call this box 0. I could encode information, one classical bit, by putting the electron in box 1, or I can move it over to box 2. But now you get the idea, right? Probably, that I can now make a purely mathematical representation of the situation here. I can say this is 0, this 0 state, and this is the 1 state. And I can put my electron into the 1 state, or I can put it into the 0 state. Namely, prepare it into the 1 state or the 0 state. But now, obviously, you know what I'm going to do next. I'm going to say, I can prepare this electron in a superposition state, indicated by the plus sign. And now if I go in and measure, I open up both boxes and I see which box the electron was in. What I'm going to do, I'm going to correct my drawing, because it's not, this drawing's not true. It's not true that the electron is in box 1 or box 2, so I'm going to get rid of that. Sometimes people like to draw it this way. They like to draw what looks like an infinity sign, but it's really called a superposition symbol. So it shows that the state, in some sense, overlaps both of them, but it's really neither. Now you know what's going to happen. If I open up both boxes and look inside, I get a 50% probability that's going to be in box 1, and a 50% probability that's going to be in box 0. So the mathematics is the same. So I think maybe we'll end there. Well, it's time anyway, but I'd like to end there with this general comment that qubits can be represented in many different ways using different physical objects. And even given an object like electron, you could represent it by the spinning of the electron, or you could represent it by the position of the electron. And then, as long as there's only 2 possible states that are being considered, the mathematics is always the same. It always looks like this little graph that we draw. So next time we'll discuss in more detail how you use these qubits to do quantum cryptography. And then a week from today, Henning Weyer will show more demonstrations showing a rudimentary demonstration of quantum cryptography using the photon generator and a few other demonstrations. So let me look in the chat window one more time. Yes, Alex asked in the chat window, this is what they say when an electron can be spinning in both directions at the same time. But as I said, that statement is simply false. It's not spinning in both directions at the same time. It's also not spinning in neither direction. It's that question is an ill-posed question from the logic point of view. The question, which direction is it spinning, is a meaningless question. It has no answer. And that's really the essence of quantum physics. It's not that we're forbidden from asking that question. Some people say, oh, you can't stop me from asking that question. I can ask any question I want. And sure, you can ask it, but I'm going to reply, that's an ill-posed question. It has no answer. So there's other questions you can ask and answer. Like, if I measure that electron, what state am I going to find it in? With what probability will I find it in the possible states? That's it. That's a well-posed question. So as far as the philosophy of the situation, not all physicists agree on what the right language is. Some people say we should have a deeper, mechanism or description. Other people say there is no deeper description, so just get over it. This is the way the world is. Change your thinking. Don't try to change the world to match your old thinking. Change your thinking to match the way the world really is. I'll leave it with that.